Okay, so in Unit 4, we cover the following learning outcomes. Briefly explain virtual memory, list and explain hardware and control structures that support virtual memory, explain the various OS mechanisms that are used to implement virtual memory, define paging, and explain segmentation. By the way, guys, my internet connection was on and off since the morning, so I don't know if it's going to disappoint me during this lecture. But if I disappear unexpectedly, just know that it's my internet connection cutting off. Okay, so these are the learning outcomes we covered. So what is then virtual memory? Virtual memory is a feature of an operating system that allows a computer to compensate for shortages of physical memory by temporarily transferring pages of data from random access memory to disk. Okay, so it's a feature of the operating system. And obviously, this falls under the concept of memory management. Okay, so I just want to quickly play this clip for you regarding memory management and virtual memory. Okay, so let's just make sure that we have all our mics muted so that we can hear what they're saying in the video. I hear someone's mic is unmuted. Okay.
In this video, we explore the need for virtual memory in a computer.
Can you hear the sound? Can somebody confirm if you can hear the sound from the video?
I can hear the sound, sir.
Okay.
And data are being fetched and executed by the CPU, they are stored in the RAM. However, this assumes that the memory is large enough to hold the programs being executed. In modern computers, it is common to have more than one program open at once. For example, here we have the operating system, and we have a word processing app taking space in the memory. However, you can store significantly more programs on the hard disk compared to the RAM because byte for byte hard disk space is much cheaper than RAM. When you turn the computer on, the Bootstrap program will load the operating system from the disk into RAM. When you use a computer, every time you double-click an icon to load a program, it transfers those instructions into the RAM. But what happens when you run out of RAM? For example, here we've got the operating system and the word processor and a spreadsheet application open all at the same time, and we've run out of RAM. Now we want to also open our graphics application, but where can it go? Well, because the computer can only execute one instruction at a time, it means that some of the instructions are not likely to be fetched in the near future. Therefore, one solution is to transfer instructions that have not been used to a space on the hard disk. This is known as virtual memory. So, for example, we could move our word processing app and our spreadsheet app out onto the hard disk, and then we'll have space for our graphics application in memory. Now, of course, in a multitasking operating system, you would want to switch between the word processor and the graphics application. Therefore, when the instructions for the graphics application are not being executed, that can be transferred out onto the virtual memory, and our word processing app can come back into the RAM in order to process the next instructions.
Quick question. What has just transpired here in the video? What term did we use to refer to this concept of what just happened? Can anybody give me an answer for that? What term did we use to refer to the concept that just happened right now in the video? Nobody remember? Remember, we referred to it as swapping. Okay, we said it is swapping in and swapping out.
So we're using part of the hard disk space as if it was the memory. We can't actually execute the instructions from there because it would be too slow. We do need to transfer them back into the RAM, but we can at least pretend that we've got more RAM available than we actually have. This enables the user to have more than a number of programs open at once, and then all still to operate, even though you don't actually have enough physical RAM for that to happen. So this gives the impression that a computer has more memory than it actually has. Virtual memory is needed when there's not enough physical RAM to store the open programs. Virtual memory is held on the hard disk. Programs are transferred out to virtual memory from the RAM when they're not currently being executed, and programs are transferred back to the RAM when
Yes.
virtual memory is needed.
Share my account.
To understand the basic principles of why there's a need for virtual memory.
Okay, so that was just a basic animation of how this concept of virtual memory works. Obviously, during our classes, we go more in depth because we talk about pages, we talk about segments, and you can see from the video, the animation in the video, that there was nothing about pages and frames. And so the concept is not as straightforward as we think it is, but it's good to know in basic terms or in basic principles how to define virtual memory. To say it's a feature where if there's not enough physical memory in the computer, then there's a need to go borrow it from where? From the hard disk. Okay, so for you to be able to support virtual memory, you need to ensure that the hardware itself supports paging and segmentation. Okay, because paging and segmentation are a key part of virtual memory. So your hardware must be able to support it. Hardware, namely being the hard drive and the CPU. But I can guarantee you modern hardware now would support these concepts by default. Operating system must be able to manage the movement of pages and or segments between secondary memory and main memory. Okay, so even the operating system itself, it must be at the core of this process of creating virtual addresses. So your operating system must be able to support memory management, being virtual memory, and the hardware as well must be able to support paging and segmentation. So these are the key terms that we spoke about or that constantly come up in the study unit, okay? And we already defined what virtual memory is. It says a storage allocation scheme in which secondary memory can be addressed as though it were part of main memory. The addresses a program may use to reference memory are distinguished from the addresses the memory system uses to identify physical storage sites. Okay, and program-generated addresses are translated automatically to the corresponding machine addresses. So this is done through that mapping concept. And then they also talk about virtual address. Okay, what is the difference between a virtual address and a virtual address space? A virtual address space is a storage allocation. The virtual address is the address of the process within the secondary disk. Okay, so virtual address and virtual address space. A virtual address space is the actual space assigned to that process. Then you also have address space and real address. So address space talks about the storage allocation, okay, of a process within the RAM or the frame. And then real address is the location of that particular process within the particular RAM, okay? So we're talking about the actual space and the actual assigned process and the address that it's assigned to. And then we also spoke about the execution of a process. And I said to you guys, do not mistake this for the instruction cycle. Two different things, okay? So what happens when a process is executed on a computer? Operating system brings into main memory a few pieces of the program. This could be a forced thing, or it could be done by default. And what do I mean by this is, if there are 6 frames of main memory and 6 pages of a of a process. In terms of simple paging concept, all of those pages are sent at once. Okay, somebody has their mic unmuted, guys. Please mute yourselves. You can ask your
Muted.
question. Who is that? Okay, so what I'm saying here is that the operating system, okay, they say the first thing that happens, operating system bring into main memory a few pieces of the program. And I'm saying to you, why a few pieces? Why not everything? It may be forced or it may be doing that by default. Okay, so if a memory has 6 frames and a process has 6 pages, okay, in terms of simple paging, it'll send everything all at once. But when you go to dynamic, okay, or virtual paging, it means that it only send a few so that it does not hog everything in the RAM, okay? It does not hog all the frames. And it allows other processes to be able to use certain parts of the RAM as well. So they're assuming that this system is using dynamic loading, okay? Because they say only a few pieces. It's going to send only the pieces that it needs executed now. And then when the others require execution, will be brought in later on. So most modern systems, operating systems, will do that because they have to allow for multi-programming. So sending all your simple paging is a very old concept. Now there's a need for virtual paging and dynamic loading of pages. So they say that the resident set portion of the process that is in the main memory. So those few pieces that you just sent to the main memory for execution, they are referred to as the resident set. Okay. And then they say an interrupt is generated when an address is needed that is not in main memory. Okay, so in your assignment, your first assignment, you were asked about the different classes of interrupt. Okay, so we said interrupt are generated in various ways. Does anybody have a question? Because I think I can hear a mic that's unmuted.
The question, sir.
Is there someone who then whose mic is unmuted because it's really disturbing me while I'm speaking?
The William person.
Okay, so how about we do this? Whatever questions you have, you note them down on a piece of paper where you are, and I'll have to mute all mics for now. So you note all your questions on the paper, and then at the end of the lecture, we will have time to ask questions because we cannot go on like this. Okay, so an interrupt is generated when an address is needed that is not in main memory. Okay, so we are saying certain things can interrupt the CPU while it's doing work. That's including faulty hardware. That's including a mouse or a keyboard or input-output request that needs attention. Also, software programs trigger interrupts. Okay, so they say that an interrupt is generated when an address is needed that is not in main memory. Because remember what happened in the first step. In the first step, we sent a few pieces of the program. Now the CPU is doing its work and it realizes, wait a minute, there are certain parts of this program that are missing or certain segments. Then it's going to trigger a interrupt on the CPU because now the CPU has to attend to something that we call a page fault. Okay, so I'll save this for the later slides in the lecture. And then they say operating system places the process in a blocking state. Okay, so because the CPU is still fetching other pieces of this process from the mapping table and from the secondary disk, it means it's going to place that in a blocking state. So they say pieces of process that contains the logical address is brought into main memory. So okay, that piece that was missing or those pieces that were missing were then brought into the main memory, and then obviously the process is then unblocked. It's put in an unblocked state, and the CPU continues executing it. What are the advantages of breaking up a process into pages or into segments? More processes may be maintained in main memory because we moved away from uniprogramming operating systems into multi-programming operating systems, which means with multi-programming systems, that user program area is going to be shared between multiple applications. So there's a need to break up a process into multiple sections, whether you call it pages or segments at this point, doesn't really matter. But there's a need to break it up, and more processes may be maintained in main memory because of that. Only load in some of the pieces of each process, okay? With so many processes in main memory, it is very likely a process will be in the ready state at a particular time. A process may be larger than all of its main memory. So these are some of the reasons, okay? A whole process can be larger than the whole main memory, okay? They tell you to play this game, you need 8 gigs, but you have about 6 gigabytes, okay? So that's the need to break it up, break this thing up so that we acknowledge the fact that this user cannot send all of this game into the main memory. You can't send 8 gigs into 6 gig RAM, okay? However, it will be able to accommodate it because it's broken up into smaller sections, your program. And so this is how paging would look like, okay? That video that I played in the beginning, they showed the different processes very well in the animation, but they didn't show how things are divided into pages, okay? So you'd have this, I would refer to it as because it's not labeled as RAM, I think it would be something like, okay, we can assume it's frames. It's frames, okay? So all of these process A1, process A2, process A3, and process A4. Once you click on each individual process on your computer, it is divided into pages. You can see that it's sectioned, and pages are equal in size. They are fixed variable length, okay? They're fixed length. They're fixed length block of data. They are fixed, and they have to be same size as the number of frames there, okay? So look at the length of the frames, and then the pages will also be divided based on the length of the frames. So again, demand paging. Demand paging is a way of ensuring that this CPU is used efficiently, okay? Because we do not want to send everything all at once. Okay, we want to load certain pages on demand. Okay, so when the CPU then discovers that there's a portion of the program that's missing, it's gonna do a fault and go and retrieve it. This allows the frames to be shared by more programs at once. And segmentation as well. It means the program is divided into segments, which is different from pages. Pages are fixed length. Segments are not fixed length. They are variable length, which means they vary in size. Okay, and so you can see that the program is divided into its sections, and it's put in non-contiguous frames. Okay, so that's the difficulty of having variable block length addresses, is because it's going to lead to what? To non-contiguous allocation spaces, because there's no way for this thing to sort of predict the RAM, to predict how big a segment would be when it arrives, okay? So there is that concept of dynamic partitioning of the RAM. And same thing applies with segmentation. There could be demand segmentation. They say demand paging is generally considered the most efficient virtual memory system. Demand segmentation can be used when there is insufficient hardware to implement demand paging. OS allocates memory in segments, which keeps track of true segment descriptors. Okay, so demand segmentation as well. So certain segments are sent, certain segments or left behind. When they are required, then they are requested, okay, from the secondary storage. And then we also talked about the memory management unit. And this is a hardware component similar to the CPU and the RAM. It's actually on the motherboard, okay? And the main role of this particular component in the computer is to manage or map addresses, resolve, translate. It translates addresses. What addresses does it translate? It translates physical addresses to the appropriate virtual address, okay, and vice versa. And you can see here that there is a diagram of the typical components we know of in the CPU, the registers, the ALU, the control unit, okay? And then there is what? There is the MMU, the memory management unit, and it contains a couple of registers, okay? Memory data register, memory address register, okay? And then there is that mapping table that will also contain the different mapping tables for the different processes, so that it's able to translate, okay, these different addresses. It's mapping physical addresses to virtual addresses. So this page table is what you would find in a memory management unit component, okay, of the computer. There could be various page tables for the different processes, okay. So the page table basically tells the computer where are the pages located, okay, because remember the CPU, when it needs to fetch or demand certain parts or additional parts of a process, it has to go back to the MMU and get that information, okay? So in the MMU, memory management units, there's going to be a paging table which contains that information, and I think it's going to come up later on as an example in the later slides. Okay, so we talked about the difference between real memory and virtual memory. Real memory exists physically, and virtual memory is created by the CPU, or it's borrowed memory. So there's something that we call the valid and invalid bit. Okay, so with each page table entry, a valid and invalid bit is associated. Okay, and what this means is that, I'm just going to move to the next slide so that you can see it. So we said in a typical process of executing a program, a few pieces are sent to the main memory, not everything, a few pieces of the pages. So when those pages are sent initially, they'll be assigned a valid and invalid bit, okay? Obviously there's a paging table in the MMU, as I said in the previous slide. So the paging table is there to map everything together, okay? So we sent these pages to what? To the RAM, and these pages are now in certain frames. So in the paging table, there'll be information about the frame number that the page is sent to, okay? And then the bits, the valid and invalid bits are there to track whether certain pages have been sent. So you can see from this example here that this process has, let's assume 1, 2, 3, 4, 5, 6, 7, 8 pages in total, but it's already sent the first 4, which means the paging table must be able to keep track of which pages have already been sent. Okay, so that when a page fault is triggered, the CPU knows that it needs to fetch now the next 4 because the first 4 are already residing in the main memory. Okay, so that's how the memory management unit is in charge of, it's housing all of these paging tables, okay? And paging tables help us to map these different addresses, real memory to virtual memory addresses. So a page fault, again, a page fault is caused by a process not finding other parts of the program in the main memory, and it has to look in the MMU, okay? So when a CPU is not, it causes an interrupt for the CPU when it can't find the other parts of a program in the main memory. So then it triggers a paging fault. And the paging fault forces the CPU to go into the MMU component, or the memory management unit. And the memory management unit, okay, which is not to be mistaken for cache memory. It's something completely different. But the memory management unit has the paging table, and it will tell the CPU that, oh, okay, you already have the first 4 in main memory. Then perhaps you're looking for these 4, the next 4. So once the CPU has found the missing pages, it then what? Then the pages are sent to main memory, and these bits, okay, the invalid bits are now turned into valid bits. Okay, so these change to 1. The next 4 now changes to 1, which signifies the fact that it's now present in main memory. Locality of reference, a phenomenon in which a computer program tends to access the same set of memory locations for a particular period of time. Locality of reference refers to the tendency of the computer program to access instructions whose addresses are near one another. So the addresses, the first 4 were sent, okay, initially. The last 4 weren't sent. It triggered a page fault. Now the next 4 were sent into the main memory. Now there's locality of reference because all the pages of this particular process are in one location, which means the next time the CPU is executing this process, it shouldn't be such a difficult task because they are all in the same location. There's not going to be any page faults triggered. So what happens then if the CPU is trying to retrieve the missing pages, but then there isn't enough frames available to put the next 4? Okay, so it retrieved the first 4 initially. Now it needs to fetch the next 4. So what happens? Then an algorithm is used. Okay, an algorithm is used to pick out which processes can be swapped in and swapped out of memory. Because remember, now we're not talking about allocation algorithms, which are different. We spoke about in the previous lecture, allocation algorithms. All allocation algorithms are applicable if there are free frames. But now if there are no free frames, it means there's a need for swapping. And how does the CPU or the CPU decide what to swap in and out? It uses an algorithm, and there's different types of these algorithm, okay? There's what we call the optimal policy. Select for replacement that page for which the time to the next reference is the longest, okay? Impossible to have perfect knowledge of future events. So it sort of assumes that a particular process has just been recently used. So the next time that the computer wants to make reference to it is not going to be anytime soon. So let's swap that out. It's just been used, okay? Which means the next time it's going to be referenced again, it's going to be a while from now. So let's remove it. And it's saying, yeah, it's saying impossible to have perfect knowledge of future events. Okay, you can't perfectly predict that the person may not trigger that same program or execute that same program again in the near future. Okay, so that's the one tricky thing about using this this algorithm, and this next algorithm is least recently used. So for the least recently used, it means that it looks at which processes have you executed previously, maybe the last 10 processes that you executed. Where can it find that information? I mean, that information is there in the cache memory. It's probably cached somewhere in the level 1 cache that these are the top 10 ones that you've executed, okay? And so it's able to replace the one that has been there for that has not, it says replaces the page that has not been referenced for the longest of time. So the one that has not been referenced for the longest of time will be the one that is there initially first in the cache. So if it's 10 cached processes, the one that's going to be removed is the first one, okay, in position number 1, okay? So the least recently used, looking at a number of recently executed processes, which one has not been referenced for the longest of time, okay? And it's most likely, because remember that cache memory can only store a limited number of processes, okay? So if you were there first in position number 1 and can only store 10, it means you are the next one to be kicked out anyway. So that's what the least recently used algorithm does. And then there's first in, first out. Simplest replacement policy to implement page that has been in memory for the longest is replaced. These pages may be needed again very soon. So this one simply looks at which one was there for the longest, okay? And then it's going to take it out of memory, and then it's going to put in a new one. And the final concept we talked about was the concept of trashing. If a process does not have enough pages, the page fault rate is very high. This leads to low CPU utilization, okay? Operating system thinks that it needs to increase the degree of multi-programming. Another process added to the system, trashing a process is busy swapping pages in and out. I just want to show you this slide. So trashing refers to a period at which the CPU spends most of its time going back and forth between the MMU and the hard disk, as opposed to actually executing the actual processes. And this happens because the degree of multi-programming has increased. So you've opened up more programs on your computer. You've opened up more programs, which means now that there's going to be more competition for frames. Okay, I'm sure you're asking yourself the question, why is it a downward sloping then, a curve, downward sloping curve? Why is it not increasing gradually? Okay, the reason for that is because you will experience this increased degree of multi-programming as you're opening more programs, and then trashing will kick in. Now, you get the downward slope when virtual memory starts to kick in. Virtual memory is there to stabilize the condition. Okay, so as virtual memory is kicking in, then the amount of trashing would decrease. Okay, so we're saying, let's take an example where you're only using one program on your computer and the RAM has 6 frames. Okay, so 6 pages, 6 frames, no problem there. Okay, simple paging, send all the 6 pages to the 6 frames. You open up a second program. Okay, now there are 12. There are 12 what? Pages. Okay, and no longer six pages, but there's only 6 frames. The frames remained constant the whole time. They didn't change. Okay, but you open up an additional program. So then what must happen? Then obviously swapping will come into effect. Okay, perhaps then the slope starts to increase here in this graph. You might have not reached your trashing period yet, but the slope will definitely increase because you've increased, but the fact that you opened up a second program, you've increased the degree of multi-programming. The frames remain constant, but the number of pages has what? Has increased by 6 again. And now you execute 2 more. Now you have 4, which means how many pages you're going to have? You're going to have 24. But what remained the same? The number of frames, which means as your degree of multi-programming increases and your frames remain the same, obviously, because they are physical, they won't change. It's physical, it's a frame. Your memory, your RAM didn't increase, but the number of programs opened up increased. It means there's going to be more competition for the number of limited frames. Okay, so maybe then after we've opened up 4 programs, you've increased the degree of multi-programming. Now trashing starts to kick in, because the CPU would then need to clean up these number of frames. Okay, if previously when you only had 2 programs, program 1 was taking up the first 3 frames, program 2 was taking up 4, 5, and 6. Okay, what needs to happen now? There are 4 now. There's more competition, more pages, which means maybe the first program will take the first one, the second program will take the second one, and the third program will take. So each program will be given 1 frame now instead of 2 or 3 as how it was previously. Okay, so the whole concept of trashing means now, for the mere fact that less pages of all of these different programs are residing in the main memory, which means there's a low locality of reference, and the CPU will then spend a lot of time doing back and forth trips to fetch additional pages for all of these processes. And also there's going to be more page faults that are going to be triggered. Okay, because remember, a page fault or a page interrupt occurs when there is not enough pages of a process within the main memory, so it has to go back to the MMU and the secondary storage to ask for those missing pages from the page table. Okay, so that's the concept of trashing. And then in conclusion, we said desirable to maintain as many processes in memory as possible. Free programmers from size restrictions in programming development. So thanks to these concepts of trashing and virtual memory, the CPU is able to make a plan for itself. Okay, and then it frees the programmers from this restriction of saying, oh, we're scared, what if our program is running at the same time a resource-heavy programming like Photoshop is running, okay? What then happens? It means our program will crash. You don't have to worry about all of that because the CPU will handle that and it will go borrow or make a plan somewhere. So with virtual memory, all address references or logical references that are translated at runtime to real addresses, okay, through the mapping and MMU component. And they say a process can be broken up into pieces, 2 approaches of paging and segmentation. Management scheme requires both hardware and software support. Okay, so that is unit 4 covering virtual memory. So I will give you guys an opportunity now to ask any questions that you may have noted down during the presentation. Okay.